I'm going to introduce the electric field based entirely on Coulomb's law, which you saw last time, but recasting it in a slightly different language. So let me suppose that right here I have some nice, big, hefty, charged object with a charge that I'm going to call QS. S stands for source. And I'm going to recast Coulomb's law with a new language in which I'm going to say that any source of charge here creates around it an electric field. So in particular, I could pick any point, and I'll pick this point, but this is any random point, call it point P, and I can ask, what is the electric field, which we're going to always refer to by a vector capital E? What is the electric field at the point P caused by the source of charge QS? So what is the electric field right here? I have charge there, it's making an electric field here. It's making an electric field there, it's making an electric field there, it's making an electric field there. But right now I'm asking about this spot here. So I need to define what I mean by the electric field at the point P, and here's how we do it. I say, well, in reality there's no charge at P. All there is an electric field. But for me to define the electric field, the way I define it is I say, suppose that in my mind I imagine there's a tiny little bit of charge there, which I'm going to call QT. T stands for test. Suppose that I have a test charge here. What's the force on this test charge? Well, we know that from Coulomb's law, the force on this test charge is a vector that points in this direction. And the definition of the electric field is the electric field at the point P caused by the source of charge QS is given by that force on the test charge caused by the interaction between the test and the source charge. This is the force on a test charge QT at the point P divided by QT. That's the definition of the electric field at the point P caused by the source of charge QS. Now, let's think about this. And in particular, let's ask ourselves, what's the direction of the electric field at the point P? Now, if QT is positive, well, I have the force. We decided that if QT was positive, the force was pointing that way. And I divide by a positive quantity. And so the electric field at the point P caused by the source of charge QS is in a vector pointing in this direction. The electric field vector points in the same direction as the force if QT is positive. So I just turned this white arrow into my way of representing the electric field at the point P. But what about if QT were negative? Well, if QT were negative, then the force would point this way. But then the electric field would be, I would take the force and divide by QT, and QT is negative. So when I divide by a negative quantity, that flips the direction around. And so the electric field points in this direction, no matter whether QT is positive or negative. And this gives us a hint that this electric field, well, we've just seen that it doesn't depend on the sign of the test charge, but in fact it doesn't depend on the magnitude of the test charge either, as I'll now show you. Let's just use Coulomb's law. So let me rewrite the electric field caused by the source S at the point P. Let's rewrite that using Coulomb's law. So Coulomb's law tells me that this FST is given by a fundamental constant K times QS QT times a vector, a unit vector, pointing in this direction, and that this unit vector is the unit vector pointing from S towards T, divided by the distance between the source charge and the point P squared, so that this distance here I will call RST, and I divide by RST squared. So that's Coulomb's law telling me what this force is, but now I have to divide by qt, and I'm going to divide by qt by erasing it. So I divide by qt, the qt is gone. And now we see that the electric field caused by the source of charge qs at the point P, what does it depend on? Well, it depends on how strong the source is. It depends on qs. There's qs right there. So how strong the field is at this point P depends on how much charge you have over there. It's this charge that's making the field. It also depends on which point P you picked. If I had picked the point P over here that's much closer to the source of charge, then this r squared downstairs would be smaller, the electric field would be bigger. So the electric field caused by the source of charge is bigger close to the charge, it's smaller farther away. It also depends on the location of P because the direction of the electric field depends on this unit vector. And if I'd picked a point P over here, this unit vector would point this way. So this electric field depends on how much charge you have at the source, and it depends on where you are. But it does not depend on that test charge that I introduced as I defined it. So the way you should think about this now, this is a recasting of Coulomb's law. The way you should think about this now is, here I have a charge, qs. This qs makes an electric field. It makes an electric field at all points. The electric field that it makes at this particular point is given by ES of P. Here's my expression. And what good is an electric field? What does an electric field tell me? If I were to stick a charge Q down at the point P, then that charge QT would feel a force. It would feel a force FST P. So I'm sticking a test charge down T, QT, at the point P. And I ask, what is the force on that charge? Well, by very simply rearranging this equation, that is given by QT times the electric field at the point P caused by the source. So this second equation, which is a trivial rewrite, on the one hand, a trivial rewrite of the definition. On the other hand, this will become the way you think. The way you will think now, instead of starting with Coulomb's law as being about forces between two charges, you will separate that out into two steps. I have some charge. Here it is, qs. This qs makes an electric field. What's the field that it makes? Well, that's this equation. My source charge qs makes an electric field with this particular form. And when I look in this equation, nowhere in here is there any other charge except for qs. Yes, there's a point P, but there's no charge yet at the point P. This field is at P even if there wasn't a charge there. But what good is an electric field? What does it do? Well, what an electric field does is it pushes charges around. So you see we've separated out Coulomb's law into two parts. The first charge, qs, makes an electric field. And then that electric field pushes around other charges. If I stick down a test charge here, it feels a force. It's pushed around by the electric field, and it's pushed around according to this equation here. And these two together reproduce Coulomb's law as we saw it last time. But what we will see going forward is that this is actually a much more powerful way of thinking about electric forces, and that this electric field, at this point, you're probably scratching your head and wondering, why am I spending so much time introducing this? What you will see as we go forward is that this electric field, which is introduced in such a simple and straightforward way, is going to take on a life of its own. So we've seen what happens if I have a source of charge here. We've seen what electric field it creates. But what happens if I have more than one source of charge? Suppose that's only the first source of charge. Suppose there is somewhere over here another source of charge, which I'll call qs2. And maybe over here there's a source of charge qs3. And let's just say that this one is negative. And maybe over here there's a source of charge qs4. And I'll make that one positive again. And there's many more. And here is the nth charge, and we'll make this one negative. So I have a bunch of sources of charge, capital N of them, in fact. And now I want to ask, what is the electric field caused by all of these charges at some point? And, well, I'll put the point P, maybe I'll put the point P right there. So the question that I want to ask is, what is the electric field E at the point P, not caused just by one source, but caused by all of these n different sources? And the answer to this question is something that we know only from doing experiments. It's the last piece of our fundamental understanding of how Coulomb's law works, how electric fields are created, is to understand the answer to this question. And you can't derive the answer to this question from Coulomb's law as I've given it to you. This is a further fundamental fact about the world that we live in that we've learned by doing experiments, by making observations of how the world works. And so here's the answer. I'm going to tell you the answer now. So if I want to know what the electric field is at the point P, I start by saying, well, what's the electric field at the point P caused by this source of charge QS1? And we saw that that will be a vector pointing in this direction here. So, okay, maybe that's going to factor into my answer in some way, so let me write it down here. I've figured out what the electric field at the point P is caused by the source of charge S1. Now let me keep going. Here's source of charge S2. That makes an electric field at the point P, which, because I'm so much closer, I'm going to draw as a bigger vector. It's pointing in this direction. And I worked that out as a vector. That's the electric field at the point P caused by the source of charge S2. Well, I keep going. Here is a source of charge S3. This one is negative. So this negative charge will create an electric field at the point P that points towards the charge. So it's a vector pointing this way. And that is the electric field at the point P caused by the source of charge S3. Well, then I have QS4, so I have more charge over here. This source of charge QS4 is going to make an electric field at the point P. That's pretty small. It's so far away. It's pretty small. It's pointing this way. And I've calculated that vector, and I write it down. It's the electric field at the point P caused by the source of charge S4. That's another vector. So I've got 4 vectors written down here. And then I get the last 5, 6, 7, 8, 9. So there's going to be more vectors written down here. And then I get to the nth one, source of charge here, QSN. That will create an electric field at the point P, which is pointing in this direction towards the source of charge because the source of charge is negative. And so here I have my nth vector, the electric field at the point P caused by the source of charge Sn. Now, what is the actual electric field at the point P? The answer is that it's the vector sum of all of these vectors. I take all of these vectors that I've worked out and add them. So I take all of these vectors and add them. And if I do that, you can see that the way I laid out my charges and where I put my point P, when I vector add these 5 vectors, I'm going to get a vector P. Here's my point P again, and the electric field is going to be pointing in approximately that direction. So the electric field at the point P, which is what I was asking for, is given by the vector sum of the individual contributions to the electric field caused by each of the sources of charge individually. Now, this may sound obvious to you, but I really want to stress that it doesn't have to be this way. And in fact, there are fundamental laws of nature which don't work like this at all. If I was teaching you not about electric forces, but I was teaching you about the force between quarks, the force between quarks does not add in this way. If I have a quark here and I have a bunch of other quarks around it and I want to know what's the force on this one quark, you can't do it like this. It doesn't work this way. So this is it feels simple and straightforward, and it's what you all expected, but this is a fundamental fact about electric forces, which didn't have to be that way. We had to learn it by doing a series of very precise experiments, which have been done over many years. And last thing I want to say is that the fact that the electric fields add like vectors, that's telling you that the electric forces add like vectors. Because remember, this electric field is telling you what would the force be on a test charge that I put right there. And the fact that the electric field is obtained by vector adding these contributions to the electric field tells me that the force on this test charge is obtained by vector adding the force on this test charge caused by this source plus that caused by this source plus that caused by this source. So this vector addition principle applies to the electric forces on a test charge at the point P, just as it applies to the electric field at the point P. So the principle of superposition that I just finished explaining to you is the last part of the fundamental description of how electric forces work. Once you have Coulomb's law at your disposal, which we have then reformulated in terms of electric fields, and once you have the principle of superposition, which tells you how to apply Coulomb's law or how to figure out what field is created not just by one charge but by many, you now have all of the fundamentals that you need in order to understand how electric fields are made and what they do. And we'll stop there for today. So, we have just learned how to calculate the electric field at any point in space due to some collection of charges. Like over here, I have two positive charges, and we've learned how to do the math, how to add the vectors to calculate the electric field at any point P. Or over here, I have a plus charge and a minus charge, two sources of charge, this one positive, this one negative, and we've learned how to do the math, how to calculate the electric field at any point P. What we're now going to learn is how to represent the results of that calculation with what are called electric field lines. So let's say I figured out the electric field at this point P. Well, here's my point P. There'd be a contribution of the electric field coming from the force between the electric field from this source, or the force between this source and a test charge that would be there. That would be an electric field that points this way. Here I have the other source, it's negative. That would make an electric field here that points this way. You vector add them and you get a field that points horizontally in the x direction, like this. If I went over here, pick my point here, what's the electric field there? It's the vector sum of an electric field that points in this direction, an electric field that points in this direction, electric field points that way. What about if I picked a point here? It's the electric field of it's the vector sum of an electric field from this source that points this way, and from this source that points that way, but that's a much smaller vector because that's so much farther away. So you get an electric field that points a little bit downward curved relative to what it would be. So you imagine now that you've gone and done the calculation that you've learned how to do at every point P in the whole board here. So everywhere on the board I have a vector. That vector tells me the electric field at this point, or at this point, or at this point. And now I join the vectors into lines. And those are electric field lines. So when I do that calculation here, I get this pattern of lines. When I do the calculation over here, I get this other pattern of lines. So what do these lines tell me? Well, if somebody tells you this is the electric field caused by a plus and a minus, what are they telling you? They're telling you that at this point, the electric field points in the direction of the line, in the direction shown by the arrow. At this point, the electric field points this way. At this point, the electric field points this way. At this point, the electric field points this way. So these lines with the arrows on them tell you the direction of the electric field caused by whatever source charges we're talking about. So over here, point P, the electric field points this way. So several basic facts about electric field lines. First of all, they never cross. That is obvious once you think about their definition. The electric field lines are telling you about the electric field at a point, and the electric field at a point is one vector at that point, so there's no way that there could be two lines crossing. That would be two vectors at a point. That makes no sense. So a very basic fact is that electric field lines never cross. A second basic fact is that the electric field lines flow out of positive charges and flow into negative charges. Why is that? Well, that reflects the fact that near a positive source charge, if I were to put down a positive test charge, it's going to get pushed away. That means that the electric field is pointing away from the positive charges. The electric field lines flow out of the positive charges. Similarly, if I think about a negative source charge and a test charge near it, if that test charge is positive, it's going to be attracted to the minus. That means the electric field is pointing towards the minus, so the electric field lines flow into the negative charge. As you start to get an intuition for this, you no longer need to do the big calculation and all the vector addition to get an intuition for how the lines will behave. Once you've done this calculation, started to gain intuition, you realize that, oh, I have a plus charge here, lines come out of it. I have a minus charge there, lines go into it. And then I join the lines, and it's going to be a pattern like this. Or over here, I have a plus charge here, lines come out of it. Plus charge there, lines come out of it. The lines can never cross. I'm going to join the lines, and it's going to be a pattern that looks like this. So at a qualitative level, I know how this pattern's going to look. I know how this pattern's going to look without doing any calculation, once I have an intuition for how electric fields and electric field lines behave. Of course, if I wanted to do this quantitatively, if I want to know what is the electric field here precisely, quantitatively, then we do the calculation that we learned how to do last time. But for qualitative intuition, once I know where the source charges are, once I know how electric field lines behave, I know how to draw this picture in a qualitative way just from the basic features of electric field lines that I've tried to explain just now. Thank you.